Section 13.6 is called starting characteristics of a squirrel cage motor. And what we want to look at here is we want to understand what is going on internally in this motor. And what we'll see is that the motor has certain characteristics. We're going to incorporate all this stuff that we had downstream into this idea. And what we'll be able to take away from this is, when you get to interacting with AC induction motors in actual applications, you will observe this. And you can also have data sheets that will have graphs that will show this. But this is, one of the few opportunities in the way the course is structured. And you don't get this, in a lot of, just fundamental motor courses. But what you'll be able to take away from this is an understanding of why the motor acts a certain way. Okay, so let's step through that, and again, when we get finished with this, we'll have equations that will relay this information. And of course, we don't reinvent the wheel every time we need to make some sort of determination to quantify something. But it's always good to be able to have that fundamental understanding of why things are a certain way. So I'm going to use this figure, what is this? This is figure 1311 as something we'll just kind of reference as we walk through this starting characteristics sequence. Okay, so what we've done initially is we have connected 3 phases of AC to the stator of this motor, and we understand how the phase groups are laid out for the 3 phases to get the magnetic field. Okay, now he says the rotor is locked. Okay, well, that means it hasn't started to turn yet. That's what you call the starting condition. Rotor's locked. Okay, so this revolving field that is created by the stator is cutting across the rotor bars, and it's inducing a voltage in each one of them that we related to this, right? And in relative terms, this velocity is at its maximum at start because the rotor hasn't started turning yet. So the rotor's 0, the synchronous speed is whatever that speed is at that point. So that relative velocity, between the magnetic field and the rotor at that point is going to be maximum. Now, when it starts to rotate, it goes down, and we understand how all that works. Okay, so anyway, this AC voltage in each conductor is cut. Each conductor is cut by an AC voltage in rapid succession by a north pole followed by the south pole. The frequency of the voltage depends upon the number of north-south poles that sweep across the conductor every second. And when the rotor's at rest, it's always equal to the frequency of the stator, frequency of the source that's connected to the stator. Okay, because these rotor bars are short-circuited, the induced voltage creates these large currents, very large currents, usually several hundred amps at startup per bar in a machine. And these current-carrying conductors are in the path of the flux. Okay, so current starts to flow. They're in the path of this. They're immersed, so to speak, in this magnetic field, and so they themselves are subjected to forces, and so those forces are the create a torque that drags the rotor around it. Okay, so he sort of summarizes this, and this is kind of what I want you to take away from this. Okay, number 1, the starting characteristics. Okay, that begins with establishing a rotating magnetic field. Okay, that rotating magnetic field induces a voltage in each of the rotor bars. This induced voltage causes large currents to flow in the rotor bars through the end rings that they're connected to. The current carrying bars themselves create their own magnetic field, and they are immersed in the stator magnetic field. And so they're subjected to these strong mechanical forces that we named Lorentz forces earlier. Okay, the sum of these forces, it's additive. It accumulates either clockwise or counterclockwise. The sum of the forces produces a torque, drags the rotor along in the same direction of whatever the magnetic field is. Okay, so I want you to take those 5 things away. Make sure that you understand that. It's very important to understand the operation and apply it to applications of 3-phase induction motors.